Such a this is of course in item not of language testing but of topography, but in language testing we know that in some gap filling tasks where you have to fill, say, 4 gaps with 5 words or sentences or paragraphs, yeah, and we leave 1 word more than there are gaps. Some people say this must be done. Well, there is no must. You are free in constructing. All we have to do, of course, is to think about the consequences. If you have 4 gaps and 4 sentences, you have another type and probably more difficulties than when you have 5 gaps in your question. And let's have a look at this. We come back to this example later on. But let's start with the easy thing, with a bit of terminology. A item is either binary or it is partial credit. A binary score can take 2 values. So the score can take 2 values. In principle, these values are arbitrary, but usually they are restricted to 1 and 0. So we say 1 for a correct answer, 0 for an incorrect answer. Could we do it otherwise? Oh yes, we could, but we have to think about the consequences if we do that. A synonym for binary items is dichotomous items. Partial credit items are items where the score can take more than 2 values. And usually the values it can take is 0, 1, 2, 3 until a certain maximum, which we indicate here by M. Yeah. This maximum can differ from item to item. And in a test we can have a mixture of binary and partial credit items. Yeah. The classical test theory is suited for doing that, and it's so wonderful that if I look at language testers, and people who know me know that I have contact with language testers, partial credit items are seldom used. Most of them use binary items, and maybe many people think that items have to be binary, but they don't have to be. A synonym for partial credit items is polytomous. Okay. Now, let's see at some examples of partial credit scoring. The matching task. What we could do is say, we do not consider the task as 4 or 5 items, as you might have think, but we consider the whole task as a single item, where the score can take several values, not only 1 and 0. For example, we say the score is the number of correct matchings. Yeah. You can say, yeah, that's the same as, because if I have 4 items, my capitals are the items, and I just say if Tallinn, let's go back to the example, if Tallinn is okay, you get 1 point, if Bucharest is okay, you get 1 point, and so on. So that's just the same. You can have 0, 1, 2, 3, or 4 items correct. That is true. So your test score will not differ by having different definitions of the item, but your estimates of the reliability, those will change. And we will see why that is when we handle the theory. Okay? Now let's look at something which is quite important here. Now we have 4 capitals. If you are good in topography, you will notice that there is one country whose capital is not mentioned, and that's Iceland. Reykjavik is missing. Yeah? So why would we do that? Now suppose that Iceland is not there. So we have now, this is my item or my task, and you have to match the capitals to the countries. The consequence of doing this is that if you make one error, for example, you think that Tallinn is the capital of Portugal, yeah, then you automatically will have a error for Lisbon, because you cannot assign Lisbon anymore to Portugal because Tallinn has occupied Portugal already. So it's impossible with such an item where the number of gaps and the number of sentences to fill out is equal. It's impossible to have one error. You have to have at least 2 errors. Yeah? And this is a bit of a nasty thing, and language testers feel that something is not good, and therefore they add a fifth possibility, and here it is quite possible to have exactly 1 error. So this is why the number of countries here is a little bit higher than the number of capitals, in order to make it possible to have more than 1 or exactly 1 error. Another example of partial credit scoring is the example where you have a text with 5 true-false questions. You might say, okay, I give 1 point for every answer, so students give 5 questions and say, this is 5 items. But you could also take another stand and say, well, if on the whole task your result is below chance level, I will give you no credits. If you are not doing better than chance, just pure guessing, I will give you 0. So if you have 0, 1 or 2 correct, your score will be 0. If everything is correct, then you show me in a convincing way that you have understood what is asked for here, and then your score is 2. And for the other cases, which is not that convincing, but is better than chance level, I give you a score of 1. You see, in this way, you are thinking about the purpose of your test, because a good scoring rule is a matter of validity. The ultimate question you have to ask here is, what do I want to do with my test? Yeah? And you have decided to develop a, say, reading comprehension test. Yeah? So you want to say something on people's reading comprehension competence, yeah? And implicit, but always there, is that you want to say that people having higher scores are more competent, are more able than people with a lower score. So what you have to ask yourself is, if I'm scoring the items and I look here at a score of 2 or 1, will I be convinced that a 2 on 5 true-false questions is a sign of a higher competence, of higher ability in language comprehension than a 1? Well, I would think no, because they are just below chance level. If you do it by tossing a coin, you will easily get 0, 1 or 2 correct, to show that you know something about your comprehension of the text where the questions are about. You have to have at least 3 or 4 correct, and you only convince me if you have all correct. Some people, and I have seen last week in the national assessment in one of our neighboring countries here, that they are on another stand and they say, okay, if we have 5 true or false questions, your score is 0 unless you have all your 5 questions correct. This seems to me a little bit too strict, and I think if you do this, that you throw away useful information. I think that people who have 4 out of 5 correct, that they show that they know something more than people who have 1 or 2 of these questions correct. So it deserves a lot of attention when you develop the test, to think about your scoring rule, because the scoring rule is a matter of validity and it deserves good thinking. Now, after these questions, we are ready to have some theory, and we will look at the classical theory. Classical theory, and you all know it, at least the first 4 bullets on this screen, has a fundamental equation. It's a x is t plus e. X is your observed score, t is the true score, and e is the measurement error. And then sometimes starts the misery. What do you mean by true score? True score is something that you deserve, is something that is created by God and that we do not know. It's something that we should know but we can't know. No, it's not that. Your true score is a statistical term. It's the average or expected score computed over similar replications. So that means, suppose I can just repeat the experiment of giving you the same test, not one time, but 100,000 times. Yeah. What we all know is that if people take the same test a second time under similar conditions, that they do not have always the same score. So if I do it a big number of times, I will have a distribution. I can make a histogram of the scores. And the average of that histogram, that's your true score. That is what you would obtain in the long run. Yeah? But I cannot see that because I cannot, the experiment is a thought experiment. I cannot administer the test a large number of times under similar conditions, because if I do it a second time, the conditions cannot be identical to the first time because you have your memory. And I cannot brainwash you to keep your memory back. So it's not possible, and we have to be very careful if we say that these conditions are similar. But as a thought experiment, it helps you in understanding what is meant by the true score. It's something, suppose I have a applicant for some job and I give him a typical task that the applicant that is successful, who is hired, will have to do a large number of times. Yeah? What I would like to see is, what will that applicant do on the average? Will he or she do this job well on the average or poorly on the average? But of course, I cannot give the same task a large number of times. Yeah? It's only once. But I would like to know what he would do or she would do on the average. Will it, in the average, be a good worker or will it be a poor worker? And I don't know. Yeah? This is the theoretical stand in classical test theory. We see something, but we would like to see what you will do on the average. And the difference, yeah, is called the measurement error. If you are doing better than you would do on average, because, for example, today you took some pills in the morning to help you look better, that might boost a little bit your average performance. But on the average in the future, you will not do this, and so I will have a positive measurement error. You will make me overestimate your average ability or competence. Yeah. Okay. This is the theory, but in some sense, this theory is a little bit trivial. It's a little bit of a tautology, because it says what I see is what I see on average plus the deviation on average. This is, for example, trivially true for the wages you have this month for your work. Your salary of this month is the salary of the average salary of whole your career plus something that deviates from the average. It's a little bit less or it's a little bit more. Yeah? But this is true for all variables. So in this sense, it's not very helpful to have the theory. But there is something more, to work out some theorems and some indices that we can use, and if we want to use it properly, we have to make sure, and this is almost never told in textbooks, and I hide it a little bit just for the suspense. Yeah, an important principle. It's a difficult one. It's called independence. Independence means, for example, no correlation. Yeah, they have nothing to do. And I will just illustrate that by showing you some phrases that are dependence. So make sure that, and always think of one person to be tested, not of a population of persons, for one person. That an answer given by that one person on one item does not imply a correct or an incorrect answer on another item. Yeah, and that's a deterministic version. And we go, as an example, we go back here to our capital item. Yeah, and I say, if you say that Tallinn is the capital of Portugal, then I'm sure that you cannot give a correct answer to the Lisbon question, because you have allocated Tallinn already in Portugal, so Lisbon should be in another place where it does not belong. So this specific incorrect answer about Tallinn implies for sure an incorrect answer on Lisbon. So these questions on their own are not independent, because if you have say that Tallinn is the capital of Iceland, then Lisbon can still be chosen to be the capital of Portugal. So it depends on the other answers if I can have some of my questions right or not. Yeah, this is an extreme example of dependency, and this is the reason why you should not make such a matching task to consider it as a collection of items in the test theoretic sense. Yeah, take it just as one partial credit item, and you will avoid a lot of trouble, and you will certainly avoid to flatter yourself with things which are not true, as we will see later. Okay? But this is deterministic. If we have it in a more probabilistic answer, yeah, make sure that the certain answer on one item does not make a correct or an incorrect answer on another item more or less likely. We have had, and it was my fault, a test where we tried to itemize a writing test. So we cut the writing test in pieces and we asked questions. Suppose that your assignment is write a letter to your friend to invite him for a party and make clear where you live and when the party is starting and if he has to bring something or not, something like that. Okay. One of the questions that we asked, well, there were two questions. One of the questions was, is the letter terminated in a proper way? And another question was, is the letter signed? Yeah. But you see immediately that someone, same person, someone who does not sign his letter, who does not put his name underneath the letter, will automatically have a 0, or with high probability will have a 0 on the question, is the letter terminated properly, because it's not a proper ending of a letter and not putting your name on it. So you see that you, by these entering these two questions who are highly dependent on each other, although not in a deterministic way, create dependence and violate the important principle of independence, which is present in classical test theory. Another way to see it, and this is a good way to look at your own test, if you develop a test, make sure that every item is a new, fresh opportunity to show one's ability or knowledge or competence or attitude or whatever it is that you want to measure. Yeah? It's a new opportunity. I have known people in making examinations for physics, and they made all their items so dependent on each other. They say, use your answer of the previous question to do the following experiment. But if your previous question was wrong, you also had a very low probability of having the current question correct. So it might have looked like very ingenious work, but from a test theoretic point of view, it's not good. So try to do that. Make your items new opportunities to show your competence. Okay? This is it. And now we will look at the graph on how it is. I have two pictures. They should be on the same picture, and the horizontal axis, as you see here, is the score on a test. The upper picture here, which is quite broad, is the true score. And suppose that we know two persons and that we happen to know their true score, and this is John and Mary, and we see that the true score of Mary is a lot higher than the true score of John. Okay? But when Mary has to answer the test, there are measurement errors. So she does not always give the same answers. And sometimes she will end up with a high score, her observed score will be high, and sometimes she will have a low score. And the blue curve depicts the distribution of Mary's answers. And I have called this Mary's private distribution. But of course, she does not give 100,000 answers. She only gives one answer to each question, so she makes the test only once. And this test, and this is important that you see it like this, the test score that she happens to obtain today is a random sample of size 1 from this blue distribution, from her private distribution. And the same holds for John. Yeah? But we see that the true score of Mary, which is just the same here, indicated by the dashed lines, yeah, the true score of Mary is higher than the true score of John. But Mary can have her unlucky day and end up in her private distribution with a draw with a very low value because she feels a little bit sick. While John feels okay today and he has, for his normal behavior, he has a very high score. So it might be that John today ends with a higher score than Mary. Yeah? So we see immediately that here we touch also the validity of our test, because we wanted to construct a measurement device such that we could say the one with the highest score is the more competent. Yeah? But if you hire John, yeah, you will have disadvantage than in the case that you hire Mary, because on the average, Mary will do a lot better than John. Yeah? And this is the dilemma where we stand for. Okay? We will come back to this later. So let it just go down in your brains, and when we need it, I come back to this same picture. Now we will see something that we usually do in classical test theory, and I will be very short on that, just a reminder of things that we have done, maybe with some new elements. One is, when we do an item analysis, is the difficulty index of the items, and it's called the p-value. You know what the p-value is, sorry, is the proportion correct of the item in the sample. Yeah? If you have an item and 70% of the sample has given the correct answer, then the p-value is 0.7 of that item. Be careful, the p-value is inversely related to the difficulty. The higher the p-value, the easier the item. Okay, but it is an index of difficulty. Yeah? But it should be low to have a difficult item, and when it is high, it's an easy item. We have to be very careful because we have a sample, and of course, if you have a sample, you have to draw it. from a certain population. Now, the p-value of an item is population dependent. Suppose that you make a test for the 5th grade, yeah, and in the 5th grade the p-value of some item is around 0.50. If you give the same item in the 8th grade, yeah, there it will be a lot easier. So the p-value in the 8th grade for the same item will go up. It will be larger than 0.50. And if you present it to another population, say the 3rd grade, then the item there will be a lot more difficult and its p-value will be lower. So you see, and this is sometimes forgotten, but it's essential that you remind this, the p-value of an item is a characteristic of the item, but not of the item alone. It is a characteristic of the item, a feature of the item in relation to a certain population. So talking about your items and giving their p-values has no meaning unless you are sure that your audience is thinking of the same population as you were thinking about. Yeah? If I say, this is an easy item, it has a p-value of 0.80. Yeah. For whom? In which population? Yeah? You have to be specific on that. And even if you are specific, yeah, then you have to be careful. Because p-values are often determined in a pretest. Yeah? And for a pretest, we need a sample. Sampling and administering tests for pretesting is expensive. You need budget, and sometimes your budget is low. So what you do is you say, well, we will take a sample from schools that we know here in the neighborhood to minimize the traveling costs and to minimize the amount of begging, because some schools refuse and we have some friendly schools who are working for us. And you draw a sample. Not being aware, for example, that if it is in a language test, that the schools that you selected from the population have very few immigrants among their students, yeah? Such that the p-value of your items might be overestimated in relation to the population where the ultimate test has to be administered later on when it is ready. So you have to be very careful on that. And then there is something, and if you have some experience with pretesting in big tests, yeah, is what we call the pretest effect. If you do a pretesting and you compute the p-values and then later on you administer the test to the population for serious where it is more high stakes, you usually will see that the p-values in quite systematic way will differ. In the high stakes test, the items look easier, the p-values are higher than in the low stakes test. So be careful when you use the p-values to compose your test to take this into account, or you might end up with a test which is far too easy in the whole population when it is applied high stakes. This has to do with probably with motivation, but be careful on that. Sometimes it is said, well, the effect is about 0.10 on the p-value. So in a high stakes test, the p-value is about, or on the average, 0.10 higher than in a low stakes test like in a pretest. This might be correct, but this effect is not uniform across items. Some items will show a large difference in p-value between pretest and high stakes testing, and others will show very few differences. So be careful with that, and well, there is no rule on how to do it. I think that you have to keep an eye on it and learn from your own experience if you are busy with that. About discrimination, some words. There are several indices used for discrimination. In the older days, we had a discrimination index, which is called, I think, D in a software program like Iteman. And sometimes I hear people say, I have a discrimination of such and such. But be careful, there are so many different indices of discrimination, when you say my discrimination index had the value of 0.30, I don't know what you're talking about. So you have to be specific to tell your audience what you mean or which index you have used. They are population and sampling dependent, just as the difficulty indices, but it's not that easy to tell what the mechanism is. The same for high stakes and low stakes. I have no experience with that, and that's my fault because I never took the effort to look good at it. But you should see if the discrimination differs when the test is administered low stakes as in a pre-test or high stakes as in a main test that has consequences for the test taking. My favorite is the item test correlation. Yeah, you can agree with that or disagree. We can maybe talk on that, but it's not that important. Okay, so these are the easy ones, and now we go to the difficult one, and I will now show you the whole screen like that. The reliability of a test score X. Be careful in your use of the words. We don't say the reliability of a test. Reliability is a feature of a test score. Just like the oh, something is going, yeah, the reliability is the reliability of a test score. The validity is not the validity of a test score. The validity is about the use of the test. The validity is about the truth and the justification of the use that you make of a test. That's the validity. It's not the validity of the test, it's the validity of your behavior when you use the test. The reliability is a feature of the test score, and when we say that, we will have to amend this. It is more, but just let's look at the definition. You remember the two sources of variation, and I have to come back to the beautiful picture that we saw here. Why do the test scores in the population, if I take a test, yeah, and Mary and John belong to the population, yeah, and I see their tests, why do they differ? I cannot see it here where the test scores are, because the upper part depicts the true score. I cannot see the true score. And the lower part depicts the distribution of the errors, but I cannot see the errors. The only thing I see is the observed score, which is the sum of the true score and the error. Okay? So if I take a test and John and Mary are in the sample, either Mary will have the highest score or John will have the highest score, or maybe they will have an equal score. Yeah? And why is there a difference between Mary's and John's score? Well, because they do not have an equal true score. That is one reason. But the other reason is that they have an error. And the error is independent. So we have to assume that John and Mary make independent errors. Is that the same as the independence that we discussed? No, it's something else. John and Mary's answers are independent on the condition that John is not sitting next to Mary and looking at her answer sheet and copying her answers. Then you have complete dependence. And we do not learn anything about John because everything that John is doing in the test is the same as Mary is doing. So we have to make sure that they act independently. Yeah? That means they have to work alone and show what they know about the material that is asked for in the test, and not how clever they are in copying other one's work. Okay? So we see that...
Norman, I'm very sorry to interrupt you. You have about five more minutes or so to wrap up.
Okay. Yeah.
Thank you.
Oh, we have to hurry a little bit. What we know about the variance, so the variance is a measure of variability. The variance of the observed score is the variance of the total of the true scores and the variance of the errors. And the reliability is the ratio of the true variance to the total variance. You see, the variance is a positive number or a non-negative number, the variance of the observed scores is always larger than the variance of the true scores. Yeah? And we hope that, as here in the picture, we hope that the variance of true scores is large in comparison to the variances of these small distributions here. A good test, we hope that the distributions here are very peaked, and that the errors are on the average not very large in comparison to the differences here between the true scores. That is the definition of the so it is a proportion, and therefore it is always a number between 0 and 1. It is the proportion of the variance of the true scores relative to the variance of the observed scores. The formula is a definition formula, and it cannot be used to compute the reliability, because all we can see in our sample is the variance of the observed scores, and the true scores you cannot see them, and the variance of the observed of the errors you cannot also not see them because the errors are not visible. So this is a definition formula that you cannot use. So what we have to do to compute the reliability of the scores, in the history of test theory, one has introduced a new concept, and that's a parallel test. And a parallel test, which we indicate by the same symbol x with an accent, and we say x prime, measures the same thing as x equally accurately, but with independent measure errors, and therefore the correlation between the x and x prime is less than 1, and one has shown, and this is something that you have to show mathematically, that the reliability, the variance of these two variants, the ratio of these two variances equals the correlation, rho is the Greek letter rho and denotes the correlation between a test scores x and the scores on a parallel test. The latter one, I will skip it. You can read it later on. Okay. So to compute the parallel test, we need the reliability, and we need a parallel measurement. Yeah, that means we need at least 2 administrations on the same sample, and this is expensive. We need a parallel measurement because we have developed a parallel form, or we use retesting. But what about Cronbach's alpha? People say you don't need a parallel measurement. You can use Cronbach's alpha and say Cronbach's alpha, that is the reliability of your test, but it is not, it's a lie. Yeah? Alpha is not the reliability except under very special conditions, and these conditions are very difficult to verify. In general, it holds that alpha is not larger than the reliability, or the reverse, the reliability is at least as high as your alpha is. Example, if your alpha is 0.95, the reliability is at least 0.95, and you say, hooray! And if it is 0.96 or 97 or 98, you don't care, you're glad. This is high reliability. Yeah? But if your alpha is 0.55, the reliability is at least 55, but it may be 0.80 or even 0.95 or even 0.99, but you cannot know this from a single test administration. The reliability is unknowable from a single test administration. Yeah? What we know from theoretical exercises is that heterogeneous tests in general yield a lower alpha than homogeneous tests. But as an index of the reliability, beware of it, it is not equal to that. And you see a lot of software packages where they say the reliability is 0.85, but they mean alpha and they don't say it. You have to know it, and that's why you are listening to me, and I'm glad to tell you that. Determinants of the reliability. Why is the reliability high or why is it low? It depends on the homogeneity of the population you are intending to measure. Yeah? The more homogeneous your population is where you will test, the lower will the reliability be. And there is one thing, you have to beware of zero scores, because some people come to a test or an examination and they hand in a blank form, yeah, and then they got a score of 0. This is okay with me. If it's your obligation to go to an examination and you don't give an answer, that your score is 0. But to find the quality of your test, yeah, the 0 score is not based on any observation because the student has not given any answers. So you cannot say that all his answers were wrong because there were no answers. But if there are some 0 scores and the test is relatively easy, the effect of the 0 scores will be that the total variance will just become larger, much larger than it deserves. And the effect is that your estimate of the reliability will go up on unjustified grounds. So look at the 0 scores. Yeah. Of course, homogeneity of the population. Yes.
I'm very sorry, I just interject there. At the moment, we don't have any questions in the question box. So for a moment or so, if anybody has any questions they'd like to ask, please write in either the chat box or the question box if you don't have both, and I will send them to Norman, and he can try and answer them.
Okay, and while you are doing that or not doing that, I will just continue a little bit until Peter. Peter is talking to me. I don't know if you can hear that. Can they hear that, Peter?
Yes, I will send the questions to you. So carry on, and while the questions come in, then I'll send them to you.
Peter was telling me that they have to stop, but they say I won't because you don't have written any question until now. So I will continue until the time is over, or unless as soon as I see a question, I will try to answer it. Okay? The homogeneity of your population is something you cannot influence, yeah, but you can influence the reliability by making better items. Yeah, I know that people who make sloppy items usually end up with a low reliability. So it's really important that your items are well considered and well constructed, and this is helpful for reliability. And the other one is the test length. That's the Spearman-Brown formula, and I will try to explain you that as the last one. Yeah, let's see what's here. You can read that formula. This cross is the multiplication sign. K is the number of items, yeah, and rho K is the reliability of a test of K items, which is given. For example, it's your test. You have made a test of 40 items, and you have the reliability. And now you think, what would be the reliability if I lengthen my test, if I make more items? Yeah? And the factor of lengthening is symbolized by F. If F is 2, that means I will double the number of items. So the ultimate test will not have 40 items, but 2 times 40 is 80 items. If F is smaller than 1, that means what is the effect of shortening the test? So it's a very useful formula. You say, okay, I have a good test, but it's too long because I have not time enough, so I will have to shorten it, and I will have to shorten it to 3/4 of its length. If you shorten it to 3/4 of its length, then F is 0.75. Yeah, and you can use this formula, and on the next slide there is an example. Yeah, my test here on top, the formula is repeated. My test has 20 items and a reliability of 0.67. What will be the reliability if I have 40 items instead of 20? Well, the first thing we do is to calculate F. F is 40 divided by 20 is 2. So we will lengthen the test by a factor 2. Yeah? And then we fill out all these numbers. So 0.67 is given, and we fill out the formula with the numbers, and it says, okay, if you have 40 items, then your reliability will be 80. Yeah.
Okay, Norman.
Yes.
Yeah, we have some questions now. If you look, can you see them in the question box?
Just a moment. Questions. Oh yes, I have question box.
Okay, and there are several questions there for you. So
yes.
Answer them in whatever order you would like. Perhaps as briefly as possible, because we are running a little bit short of time as well.
Okay. Can I have no very much. I will try to One is, I will just read them aloud. Should examinees who did not respond to very many test items or to no test items at all be excluded from data when conducting analysis? Well, there is no law on that, but just remind the example I gave you with the 0 ones. If they are not, if people do not give an answer, you can make a decision on them. It's for an examination, say, yeah, you did not give an answer, so you will not pass the examination. But if it is to estimate the quality and the reliability of your test, I would be very careful, and usually I would advise people to exclude from the item analysis examinees who respond to very few or no questions at all. Okay.
Next one.
Will there be a bibliography or a reference? Well, there is a reference in the invitation, and that's the main reference, and there are references there. And of course, everybody who is involved in tests learns something about test theory, and you have references there. There is no, I do not plan to make a special reference list at all. It's certainly not for classical test theory. With 0 scores, then the next question, should we clean out 0 scores from no responses, but keep in zeros from incorrect? Yeah, be careful. If you remove observations, you remove a student record. So if John has not answered to any question, then I would remove them. But if John has given an answer to all questions and they are all wrong, I would certainly keep him in. Because if you, this is a very good question. Huh? If you give a 0 based on your rule of scoring the item and the item is wrong, then keep it. If people do not give an answer, this is always a very difficult problem. You cannot judge it. You can judge to take a decision on that person in your, say, in your teaching circumstances, but if the focus of your activities is in determining the quality of your test, then I would, just as the first question asked, I would not consider people who have just skipped all or very many questions. So this, a lot of the questions are for this last point on 0 scores. What if there are sections of a test in which the TT, what is it, the testis has not answered any questions? Not the whole test as in your example. Does this affect the variance scores? Yeah, of course, it's a, this will affect the whole thing. If this might be relevant in situations where your test is too long. If there are people who are a little bit slow and the test session is over and they have to go for 25% of the last items, you didn't see that they gave a wrong answer because they had no opportunity to give an answer at all, and I certainly would not include them if I wanted to judge on the quality of the test. And then a last question, is classical test theory still used in tests? Is it suitable for both NRT and CRT? I don't know what is meant by NRT and CRT, but of course it's still used in tests. Even people who use, and this would be the second part, but you see I couldn't tell you about the second part now. Reliability is really at the heart of test theory, and for any test that you develop, you should try to find good answers on the question of the reliability of the test. And this is something that belongs in classical test theory. In many books on IRT, on modern test theory, the question of reliability is not even discussed, and this is a very big mistake. It should, because if you have no evidence that a large proportion of the difference that you see are really worthwhile, are stable differences, yeah, but could be just be measurement error, then you are busy with something which is not worthwhile. So classical test theory is certainly still used. And what is CRT and NRT? Can somebody write this in the chat box, or Peter, can you hear me?
Yes, I can, yes.
Do you know what is meant by NRT?
And criterion referenced.
Oh yes, and NRT is a norm reference test, and yes, of course it is suitable for both of them, for criterion and norm reference test.
Okay,
yeah, the answer is yes. So I have something more to say, which is very interesting, but
perhaps we should just restrict ourselves to the questions at the moment, because there are more coming in now. So let's try and get through these as quickly as we can.
I have seen all the questions which were in my question box. I have read and answered them all.
Okay. Okay, let me just...
and there is nothing in my chat box, and I have answered all the questions.
Okay, so I'll send you another one.
Okay. Follow-up question: how do we analyze the scores to accommodate for this difference in response? I must say I do not understand the question. How does this increase the variance? Well, suppose you have on the variance increasing thing, suppose you have a test that you administer to 100 students, yeah, and the test has 20 items, and they are binary items, so the minimal score on the test is 0 and the maximal score is 20. Yeah, the variance is a measure of inter-individual differences. Yeah? So what would be the score distribution that makes the variance as big as possible, that makes the differences between people on the average as big as possible? Well, the answer is, it is maximized, it is as big as it can be if half of your students have a score of 0 and the other half has a score of 20. Yeah? Then you have a very strange distribution, which is a kind of exaggerated U-shape. Yeah? Normally we have a single peak like the normal distribution. A distribution like that, most of the observations are in the middle, maybe not just in the middle of the scale, but somewhere close together, and we have tails, but these tails are thin, they are not very frequent, and then we have a certain variance. But if you have a U-shape, yeah, where most of the people are either very low or very high, yeah, then you increase the variance. Now if you have a lot of people who have 0 for reasons which have nothing to do with the test, and that is always the problem. Some people come to the test, yeah, and give a blank sheet in, and if you say I will count that, then you give implicitly the interpretation that these people did not know any answer to any of the questions that you asked, so you give them all a 0. And I think in many cases this is not justified, because people can give a blank sheet for other reasons. Maybe they don't feel well, or they have other reasons to, they are maybe not interested in the subject at all, but they have to come because otherwise they would lose their grant of something, and therefore they come, they put their name on their answer sheet and they hand it in to have a proof that they were there, as they should be for bureaucratic reasons. Yeah? So their behavior does not say anything on the test or its intended population, because if I'm correct in my reasoning, these students give a sign that they do not want to belong to that population. They quit the study and then they do it for just for a, yeah. So it is not that simple, and don't take my advice as a law. You have to think about it. Yeah? Yeah. Is a blank sheet or a non-answer, is it a sign of not knowing the answer, or is it a sign of something else? Not having the time to answer that, and then you have to be very careful on that. Yeah, this is always on the same topic. There is another question come in. Could you elaborate between alpha and reliability? Well, I do my best to do that. I just make this and we come back. Just give me a moment. Cronbach alpha. Yeah. Alpha cannot be larger than the reliability. Yeah. That means, yeah, I don't know what to say. It just does mean that. If your tests all measure the same thing, then your alpha comes closer to the reliability. But this is quite technical. I cannot do this in the little time we have here. It's just the general thing is that, yeah, a lower alpha comes out of heterogeneous test. I can add one thing, and sometimes people come in panic to the psychometrician and they say something is wrong with my package because I got a negative reliability, and reliability is a number between 0 and 1. Yeah, that is true, and reliability cannot be negative, but alpha can. Alpha can run from -infinity to +1. So the maximum value is 1 for alpha, but its minimum value is certainly not 0. It can be negative. And if you have a negative value for alpha, then the first thing I would advise you to do is to look if there is no coding error that might cause that some covariances between items become negative. Look always at your item test correlations. If they are negative, it's the same thing. If they are negative and they are substantially negative, like -0.20 or -0.30, you probably have a coding error in multiple choice questions. That means if A is the correct response, that in the coding in your machine you have given the instruction that not A, but for example C is the correct response. Yeah? And this will usually cause a negative item test correlation, and this will also in general lower your alpha. What you can do, and this is sometimes done in some software packages, that the package automatically will start to remove items. Yeah? Because it is possible, and usually it is so, that if you have, say that you have 39 very good items and you compute and one bad item, and you compute Cronbach's alpha with these 40 items, and then you remove that bad item, say with a very low item test correlation, and you remove it from the test, that your alpha with 39 items is higher than your alpha with 40 items. So it is not true that saying if there is a bad item in the test that doesn't matter very much. It does matter because bad items will lower the reliability of your test as a whole. Yeah. But on the other hand, be careful, because it is sometimes possible that removing items with the has the consequence of making your test more homogeneous, so that the items are pointing to the very same but narrower construct than originally meant. So what you do then is to break down your content validity, and if you break down your content validity, you break down your construct. Yeah? You change your construct to enhance your reliability, and this is not always the case, because the reliability can be high instead of alpha. The only thing you really can do, and if it is a test that is really important, you have to organize in some way a parallel test. It's always good if you have the means and the resources to do this, to develop for important tests from the very beginning a parallel test. So you don't make questions, you make pairs of questions or even triples of questions. Yeah? And if you have enough items after a pilot, you can assign the members of your pairs to the original test X or to the parallel form X prime. And then you have to find examples that take both forms, and you compute the correlation. And this is a genuine, and it's almost the only good indicator of the reliability. So just hanging on alpha is not good. I know that it might hurt some people, but it is like it is. And the fact that in many textbooks it is said that alpha is a reliability does not make this true. It is not true. Peter, I think I'm done. We are 15 minutes over time now. What do you think? Peter has fallen asleep. Peter? Hello?
Yes. Yes.
Oh, sorry. I think we have to stop now because we are 15 minutes on time limit.
Yes. Okay. Well, thank you very much, Norman, for a very informative and I hope very useful webinar for everybody. Thank you for attending, everybody. And as I mentioned at the beginning of the webinar, we will be sending around a survey monkey asking for suggestions for future webinars. So please respond to that if you're interested. And this recording, most of the recording, we had a slight technical hitch at the beginning, but most of the recording will be available on the EALTA website next week. Okay, so until the next time, have a great weekend, and thanks very much for attending.
Thank you. Goodbye, everybody.
Bye.
Bye.
Wait, let's come back on there. Bye, everybody. Have a good weekend.
Is everybody gone? We are alone? Peter?